Lecture 6, first one in Unit 2, Atoms, Molecules, Ions. We're going to start just looking at the atomic structure at the beginning of this packet, and by the end we're going to be reviewing nomenclature. Nomenclature is pretty important. We see it again in the review of 10 big things from AP Chem. If you have any questions on your questions, please email, let me know, and I'd be able to post anything you need. Beginning right now, let's talk about atoms. Back in the day, ancient Greece, people were like, no. There's no way everything can be made up of the same stuff. It's illogical. Okay, well, this guy Democritus was like, well, yeah, everything's made up of the same stuff, little things, little atoms. And all of the important scientists were like, pfft. And in ancient Greece, when the important people tell you, pfft, you say, okay, pfft, and you go away. So for a long, long time, people said, pfft, to the atom. Until 1800 with John Dalton. Dalton was a scientist back in the day when you weren't like a physicist or a chemist or a biologist, when you were a scientist. So we'll see Dalton's law of partial pressures coming up in gases much later in the year. But Dalton wrote the first modern atomic theory. He linked the idea, and here's your blanks, he linked the idea of elements with the idea of atoms. The elements were being discovered. Mendeleev came up with that full periodic table by 1865. But the idea of elements, at least the big ones, nitrogen, oxygen, carbon, hydrogen, was out there. Dalton put that idea with atoms. Here are your fill-in-the-blanks part of his 4 parts to his atomic theory. Each element's composed of extremely small particles called atoms. Cool. I believe it's from the Greek word for indivisible, atomos. I think that's where that comes from. All atoms of a given element are identical, but the atoms of any one element are different from atoms of all other elements. Okay, well that makes sense that you'd have some different stuff going on. Atoms of one element can't be changed into atoms of a different element by chemical reactions. So reactions aren't changing atoms. Atoms are neither created nor destroyed in chemical reactions. Compounds. This is how he justified what he was seeing going on with the atoms aren't created in chemical reactions, but they rearrange. Compounds are formed when atoms of more than one element combine. Given compound always has the same relative number and kind of atoms. All right. Sounds great, but it's a theory. So there is room for us to say yay or nay to the parts of it. There are a few parts that modern evidence has said no to. In number 2, all atoms of a given element are identical in one way. Protons, your number of protons identifies an element. That's the number you find it at the periodic table. Hydrogen's 1, helium's 2, all that good stuff. But atoms of the same element can have different numbers of neutrons. Those are called isotopes. And with ionization, number of electrons can change. So atoms of nitrogen aren't always exactly the same, but they will have 7 protons. Number 3 is iffy. Atoms of one element can't be changed into atoms of different elements in a chemical reaction. Nuclear fusion, nuclear fission, center of stars, hydrogen bomb, colliders, where we're launching 2 atoms at millions of miles, not millions literally, but lots of miles an hour, around a tube to collide them and make new elements. The heavier elements, like oganesson and tennessine, are made that way. Is that a chemical reaction? What you call that reaction depends on if you think Dalton's right or not. I don't think of that as a chemical reaction. I think of that as a physical merger or a physical change to the nucleus rather than a chemical change. Taking apart the protons or adding to the protons. If you think that's a chemical reaction, then Dalton needs to redefine that. Dalton also thought the atom was like a marble, like Democritus did. That's not included in his atomic theory, but it was one of his thoughts, and that also we know is incorrect, just with the existence of protons, neutrons, and electrons. Existing laws were explained by this theory. Your law of constant composition is another name for your law of definite proportions. It says in a given compound, the relative number and kinds of atoms are constant. Water is always H2O. We did that in the last packet. He explained this. Dalton explained this. A given compound always has the same relative number and kind of atoms. He discussed that in his theory. Law of conservation of mass. Matter is neither created nor destroyed in ordinary chemical reactions, says Dalton. That's exactly what the law of conservation of mass says. The mass of reactants I start with equals the mass of products I end up with in an ordinary chemical reaction. Physicists do conservation of mass energy for some of the crazier reactions where small amounts of mass are either lost or gained as energy. With the number of significant digits we're looking at, with the reactions we look at, we don't do mass energy in chemistry. We just look at law of conservation of mass. But I will put that out there as a note for any of you who are taking physics. Expect to see a change in that in your upper level classes. Law of multiple proportions is new. If two elements A and B combine to form more than one compound, like NO, NO2, N2O, you can do all of those. If two elements A and B combine to form more than one compound, the masses of B that can combine with the masses that can combine with a given mass of A are in the ratio of small whole numbers. This is messier than it sounds. The calculations are a couple different steps, and we will work through one of those in a problem. But what it comes up with is once you're done, you've always got comparative masses of B, like AB2, AB3. You'll see the 2 and 3. You'll see the comparison. So law of multiple proportions basically guarantees whole number ratios of atoms combining. That's what it comes down to. Lots of words for that, but it is. Structure of the atom, building the modern image. Important things to know. Big things with charges. Like charges repel, opposite charges attract. So plus, plus, and minus, minus repel. If I have two magnets and try to jam the positive poles together, they kick off. Two negatives together, same, they'll repel. But if I put the positive end near the negative end, they're like, perfect, and they stick together. My dad had bar magnets he used to have a feed store when I was growing up. And that was always, I don't know, I loved that. I loved playing with the magnets. So that comes into play a lot with how a lot of early discoveries of the atom were made. Cathode rays. Cathode ray tubes, there ain't much in them. They're a glass tube with a positive and a negative electrode, pumped almost empty of air. Your cathode is your negative electrode, and your anode is your positive electrode. I know cations are positive. I know that seems weird. Cathode is negative electrode, anode's positive. You only see the cathode ray. If you look at the picture, there's the line going across. You only see that when voltage, V-O-L-T-A-G-E, voltage is applied to the tube. So your cathode ray is only present with electricity there. It travels from the negative electrode to the positive electrode. When you first run the electricity, you see it going there. And it's not light. It looks like light, but it's attracted to a magnet. It'll pull up on the positive end of a magnet, not the negative end. It attracts to the positive magnet. What is it? It's electrons. J.J. Thomson, 1897, described cathode rays as streams of negatively charged particles, credited with discovering the electron, because that's what they were. He didn't have a word for it yet. He didn't know a lot about it, but he said, there's these negatively charged things in atoms. Look, it sucks to the positive end of the magnet. It's only kind of true that he discovered the electron. What he discovered about the electron was its ratio of charge to mass. Coulombs, capital C, is the unit of charge. So every gram of this stuff he discovered had a charge of negative 1.76 times 10 to the 8th coulombs per gram. You'll also see this without the negative, but I figure since the electron's charge is negative, we're good there. Do you need to memorize this? No. But it shows that the negatively charged electron was for real, and that the amount of negative to it was able to be measured. Robert Millikan wrapped this up. Oil drop experiment, big one, oil drop. What Millikan did with that experiment was calculated the charge of the electron, the charge of an individual electron, not just saying, hey, it's negative. This value, there it is, negative 1.602 times 10 to the negative 19th coulombs. We'll see later, we could just call it negative 1 because the ratio is always the same. Combined with Thomson's info, this gave the mass of the electron, because if you combine coulombs and coulombs per gram, you can get the electron's charge at negative 9.10 times 10 to the negative 28th grams. They combine pretty nicely. Awesome. Up till now, though, we've got this problem with the atom where, yeah, it's positive, yeah, it's negative. We see that. But Thomson's plum pudding model was sort of the big idea. Plum pudding, puddings in England are bread, a lot of times with fruit floating in them. Think fruit cake. I always say think Jell-O fruit cups, where you have the goo and the little bits of fruit in the goo. That's basically what Thomson said about the atom. He said it was a uniformly positive sphere of matter in which electrons were embedded like raisins in a pudding. Raisins in a pudding is like fruit in a fruit cup, like seeds in a watermelon. That's probably way better. So he thought that the protons and everything was scattered all through. He didn't even know protons. He thought it was positive and negative all over the place. Cool. But Rutherford said, Rutherford shot these things called alpha, ALPHA particles at gold foil. Alpha particles, it's like naked helium. You take the electrons off helium and leave the positive nucleus. So it's a positive particle. Rutherford launched these at gold foil. He thought either A, they were all going through the foil, or B, the negative electrons were going to snap them up and they were just going to live in the atom. He realized the atom was mostly empty space, that it kind of had to be because it was really small and really light and just not that exciting. So why not mostly empty space? We'll go with that. They're going to go through. His grad student noticed something up with his experiment. Rutherford gets the credit, but the grad student actually did it. The grad student noticed that once in a while, a particle would fly back toward the detector. And that didn't seem right. Rutherford thought that everything would go through and say, oh, look, empty space. The particle that kicked back to the detector when the experiment was analyzed and thought through, what had happened to that particle is that it had come near the positive nucleus. There's a lot of positive charge jammed in a very small space in the nucleus. So the particle that kicked back, positive particle too close to a positive nucleus, was repelled. The particles that traveled through hit the gaps around the nucleus in gold foil and were able to pass through and be picked up by detectors on the other side. Rutherford was very surprised that the delicate atom was able to kick back a particle. What he discovered from this is what we call the nuclear model of the atom. Not nuclear like boom, nuclear like having a nucleus. What the nucleus contained, according to Rutherford from his experiments, was most of the mass of the atom. We now know it's because of neutrons and protons. And the positive charge of the atom. That's your 1 and 2 in your notes. And the volume of the atom is mostly empty space. Rutherford didn't discover the proton per se yet. He had more experiments to do, but 1919, Rutherford says, yay, proton. That's what's in the nucleus. Rutherford wins. Rutherford gets the proton. Chadwick, he was a little later, but if you think about it, we talked about protons and electrons, and the mass of an atom comes from more than that. People were coming up short on mass calculations. If you just counted protons and electrons, there was other stuff in there. 1932, Chadwick discovered the neutron, the particle with no charge that made up the rest of the mass of the atom. And that's how we got our currently accepted model of the atom. Lecture 6 done.